I don't even remember what that's from. It's from some D-bag.
It's I thought it was Bill O'Reilly, but it might not be. It might be Chris Williams. Fuck it, we'll do it live.
Fuck it, we'll do it live. We'll do it live. Well, we're fucking doing it live now, aren't we?
Yeah, right. Well, so we just dropped the F-bomb like 3 times in the first like 5 seconds. So...
Yeah, but I'm Canadian. I was talking about seals, so suck it, YouTube.
Right?
Yeah.
Okay.
All right. I get rid of my virtual background. Because I may or may not need to draw something on a whiteboard, and you know, that's a thing that happens when you've got Dr. Tap here.
Yep.
If Andy makes me want to get out a colored marker, and explain what I don't understand. So Dr. Tap, everybody knows you because you are the Penta Weezell. Right? There's no other Penta Weezell.
Not that I'm aware of.
No, you're the lore, the comic book that would be made about you would be like a cross between the Punisher and Alvin and Chipmunks, essentially.
Mm-hmm.
I think that's a fair statement.
I don't know what a crossover between the Punisher and Alvin and the Chipmunks would look like, but I really, really want to watch it.
I think we all do. I think we really all do. And
I mean, that sounds absolutely enthralling.
I think it would be.
Yeah.
I remember watching a weird documentary about Alvin and the Chipmunks and the people that voiced it for the sort of the live action crossover type movie they made, that it kind of hit when my kids could enjoy it. And I remember that cartoon being on when I was pretty young, like young enough to know about it and watch it a bit. And apparently the singers do everything super slow so that it's enunciated slow and clearly, and then they speed it up to get a song that's sung in that super high pitched voice, but not super fast. Because that chipmunk effect, when you play people super fast, we could talk about that because that's actually like piling waves on each other. But those are sound waves, not photon waves, which are different but similar. And we're gonna get into that. So but I remember learning about that and thinking that's kind of cool, because if you just sped it up, you'd have people singing about the damn witch doctor so fast that it would just blow your mind. And and like nobody wants to hear somebody in a high pitched voice say ooh ee ah ding dang walla walla bing bang really really fast, because otherwise you there's something lost if you speed it up. Right?
Yeah. It's there's only so fast, for example, that you can listen to a YouTube video before you can't like understand it anymore. I don't. There are people that like listen to everything by default on like 2x speed, and I'm like, I can't handle that. That's too fast.
I can't either. I first learned about that for like audiobooks, and I'm like, you know what? I got time to hear it.
Yeah.
And I also feel like my brain works better if I let things happen at a certain speed. Now there are other personalities, and I would say ideas if they were coming from someone else. But if you take a look at there's a gentleman whose name is the same as a large center in Texas. It's actually the capital of Texas. Who his word salad comes out at a speed such that you have to slow it down to understand what hasn't been said.
He is one of the 2 best people at word salad on the planet that I'm familiar with. You're referring to Austin Whitsitt.
I'm referring to Witless word salad. Austin Whitsitt, yes.
Yeah, and it's phenomenal. Like the guy it's genuinely very impressive. The only person that I know of that comes close is Ken Wheeler.
Yeah,
and I don't know which one is better. I don't know which one. Yeah,
and Ken Wheeler's word salad might be better, but I don't think Ken Wheeler can get it out as fast as Austin Whitsitt.
Not,
like
yeah,
speed wise. I
yeah,
mean,
that's true.
Ken Wheeler, I think he makes it out of whole cloth on the go.
Well,
But
Winston does
well,
a lot of that too.
he does, but he's got a repertoire,
Yeah, but yeah, so
to
does
go.
Ken though. They
He
both do.
Yeah, and they go back to the well over and over again. And of course, they say
Yeah,
the same thing about brainiacs like yourself because
yeah, it's like,
you keep repeating the truth, and it sounds like you're just using catchphrases.
yeah, I can understand that. I can
But
understand that. But like, I can
unfortunately,
bring receipts.
the truth can be boiled down to a couple of catchphrases.
Well, that's particularly true in like physics. You can say an enormous amount of things with an incredibly small amount of word of symbols, I guess would be one way of saying it. Yes, exactly.
Yeah,
And
I don't know how to pronounce Reggio's name.
I say Regios, but I actually don't
Regios?
know. Yeah.
Regios, please pronunciate yourself for us. We would appreciate it.
Maybe it's a hard G. Maybe it's Regios.
Regios. Like I know people named Reggie and Reginald, and I think of that, but then I generally when I read this in my brain, I say Reggio, and
Hmm.
then I forget about the S, and that's wrong because and we don't know if it's plural
Yeah. Yeah.
or if it's
I
reg ios like
I have no
regulation.
idea.
Anyway, what this
Reggie. I guess
Reggie
Reggie. There
is
we
it
go.
Reggie?
That that's what they posted. So
They posted. Oh, you know what? It came. Oh, Reggie in chat. Something. Okay,
yep, yep.
mine. Like my chat came up 3 seconds after you talked. Like that was weird. Like you saw
Yeah.
because the internet is so much faster on the left coast. It came to your computer faster than mine because you know why? It's because of the direction of rotation of the Earth.
Yeah, okay, sure.
He's like, I don't know where Reggie is, but let's assume Reggie's somewhere further west than I am. And then it had to like
Yeah.
come all the way back around again.
Yeah, yeah.
Oh, Aunt Jur, this is red and black plaid is not just see there he's in Minnesota. I'm assuming it's a he. I have to stop assuming. Hi Carrie, hi Aunt Jur. Yeah, so in Canada, we like the red and black plaid is it was number one for the flag until someone drew that damn maple leaf and we got stuck with that. And I have a Canadian superhero on my shirt today. I hope you guys can see this.
Oh,
It's a
nice,
little
yeah.
faded.
Yeah,
It's a little
yeah.
faded. But like I wear a uniform shirt every day at work and I kind of like on the weekend I love getting out all my shirts that aren't uniform shirts and wearing them.
Yeah, yeah.
But yeah, you know, we have a saying here in Canada about French Canadians, and usually it goes something like this: they're like, "Hey Gaston, you know, I'm thinking I should learn French because it would go so well with my accent, eh?"
That's funny.
You know
Anyway,
that one? I forget where
I
that's from. I forget where that's from. I have my old buddy who actually
beauty
passed.
that
I don't know who he is, though.
Gaston and talking like that sounds like the Beauty and the Beast thing.
Yeah, it's kind of
Yeah.
it's from yeah, but I think it's from I think there was a thing about a couple of French Canadian like canoe tripper type guys doing like fur trading and stuff. And I believe it was an ad for a beer.
Mhm.
We used to have a lot of Canadian beer ads were I guess they were they were incorrect politically because they would make fun of people with French accents. And I'm not French myself, but I do je parle un petit peu en français, je comprends le français, je peux écrire, je peux lire en français, mais je connais aucun mot en français. Alors c'est un peu difficile de parler en français.
I have no idea what you just said.
Sacre
know you
bleu!
said I
Sacre bleu! That's what I said.
Sacre bleu!
Sacre bleu! I know how to get
Oh,
us shut down. I'll say tabernacle.
oh.
The Quebec
So,
City YouTube just like blew up right now. They're furiously typing a sternly worded letter in French Canadian French.
yeah.
Yeah. No, it's oh, Aunt Jur understood most of that. Um just so you know, Dr. Tap, because I know you're about to start speaking in a language I don't understand, but just so you know, what I said was I know a little bit of French. I can read and write in French, but I don't know any French words. And then I said, sacre bleu.
Yeah. Yep, yep. I'm familiar with Sacre
Um,
Bleu.
yeah, very strangely, I did all of my elementary and high school education in French.
Huh.
Isn't that
That
weird?
yeah, that is weird.
Yeah,
That's
okay,
pretty
for preview. Yeah, this is
yeah.
how we're gonna feel. So I don't know that anybody in the world doesn't know what Dr. Tap does for a living, because he's always bragging about having his giant brain in a little basement in Sacramento. I don't think that's where he
I'm
actually
nowhere
lives.
near
No, no,
Sacramento.
no, it's
Sacramento's like 2 hours away. I
this
actually
is
don't know how
just
far Sacramento is. This state is
2 hours. I
huge.
mean, that's like I would
It's
drive there just to
I
talk.
agree with I agree with you. Okay, I'm also from a North American country where you need a car to get everywhere, which is
Yeah,
all of
yeah.
them. um,
Jesus.
I don't know about Mexico, but yeah, 2 hours is not bad. I have like a 25 minute commute to work, and so a few years back, I think in like 2017, I went to a conference in Rhode Island, and I we went out and like went to this clam shack that they had there that was really popular. So the line for
Yeah.
the clams was like an hour and a half long. So I was standing in line with this couple also from Rhode Island, but they had like moved to Rhode Island like in their 30s or something and had lived there
Okay.
for like 30 years. And they were telling me how people in Rhode Island won't go anywhere more than 15 minutes away
Oh, yeah.
because
Yeah, and I've heard Stephanie say the same thing. I think because Stephanie's I think a member of the community who's particularly New England born, bred,
yeah,
and still lives there.
yeah. She's up in Maine, which
Yeah,
is a lot
she's
bigger.
a Mainer. She's a
Yep.
Mainer where they fish for lobster. Right next to all of my friends, and I don't have much family there except in the summertime because my family travels there often to New Brunswick.
Mm.
Um but yeah, a 1/16th demigod. I mean, um maybe he's 1/16th Demi Moore, but
Who,
uh
me?
yeah, you. Yeah, you.
I'm I I don't think I'm 1/6. I'm like
1/16th
I think I'm
demigod.
3 the thing so
But that would make you a
canonically,
1/32nd god, right? If 1/16th of a demigod would make you 1/32nd of a full god.
maybe. I know well, that would be semigod. Semigod and demigod don't necessarily mean the same thing, right?
Oh, because like en français, demi is half.
Mm, yeah.
And semi is a kind of truck. Are you
So I'm
are you
told.
following along with this?
Uh,
So so you know what? Like, so this is an interesting thing because I want to get into this conversation, and I guess people can see in the banner that I have misunderstood everything you've ever told me about what you do when you shoot a laser at a tom, right? And then did you did you like that? This is
yeah.
I hope people get the turkey hunting reference
I didn't get the turkey hunting
because
reference. I just thought it was funny that you said Atom instead of Adam.
okay, so a male moose is called a
Is it a
bull moose,
Tom?
a bull
Oh,
moose,
bull.
a
Yeah,
bull
yeah, I
moose.
knew that. I did know
Okay,
that.
a male camel is called, I don't fucking know, Clive, I think. And And then or Joe also. Male
Yeah.
Camel, Joe Camel, I believe.
Yeah.
Yeah, smoked a lot.
Yeah.
He was kind of like
Yep.
Humphrey Bogart in that
Yeah.
regard, and he always bogarted his sports sticks, his scents, right? I won't use the
Mhm.
word that I would usually use for a cigarette, but yeah. Have you ever had a Nat Sherman cocktail cigarette? They come with a colored paper. All right, well, you're missing out, man. You're missing out. When I quit smoking on February 2nd, 2005. But I was very lucky at one point in my life to smoke an entire pack of Davidoff Magnums. And Davidoff Magnums are extra large, but from what I recall, they're actually also rolled into an ellipse as opposed
Hmm.
to a circular cylinder.
Mm. Interesting.
And I thought that was kind of cool. But the Davidoff Magnum is a pretty hefty cigarette. I think it's like a demi cigarello.
Yeah.
It is like is what Moore did to cigarettes, it went in the other direction with. And
Yep.
I'm
Yep.
pretty sure nobody's getting any of these references because
I'm certainly not.
my ability to smoke and know my way around a smoke shop back in the 90s and early 2000s is probably unparalleled. Should I put on the hold music? I just found out today that StreamYard will let you have background music, but like I can't
Does it
imagine what.
really? No,
Yes,
sorry.
it was your background music.
That's hilarious.
What the
I
heck
I
is
was
this?
just I just have to like refill my water bottle.
Oh, that's all right. That's all right. I have backup. I have backup content. But I'll tell people
I
what's
can always
going
just
on.
shout.
Ever suck on the butt of a camel? That was a normal thing I heard among smokers when I was younger. Yeah. You know what? Camels, I used to smoke Camel Plains, and Virginia tobacco is a different tobacco than Canadian tobacco, which is grown mostly in southwestern Ontario, near where I live and work now. And I've actually hauled equipment in and out of tobacco farms. Not very often, but I have. And I actually picked up some equipment that was being parked on a tobacco drying equipment storage yards space. And I was like, that's a lot of dryers. And they're like, yeah, they're all for tobacco. And I was like, that's awesome. And they had like, I don't know, hundreds of them. Anyway, you gotta dry tobacco before you smoke it, because I actually learned today how hard it is to light water on fire. Um, and it doesn't like being set on fire. The components of it are helpful in fires, but when they're bonded together in in the liquid format that we're familiar with, dihydrogen monoxide, it doesn't like to come apart and stay apart. So they smoke cloves, dark. Oh yeah, I remember people having clove cigarettes.
Mm-hmm.
That was a weird thing. No, I used to also smoke Mavericks, which were awesome. Cheroots. They had a brown rolling paper. They were great. I also smoked a lot of Gitans, and I also smoked a lot of Gaulois, and I smoked them all filterless. And amazingly, I'm still alive. And I've been checked 3 times. I still don't have lung cancer.
Nice.
Yeah. And my lungs apparently are clear and do not show any signs of long-term deterioration other than my bronchial asthma, which is a problem I still have.
Cool.
As well
Well,
as
not cool.
a
That
speech
probably
impediment
sucks,
that
but
prevents me. I have this weird speech impediment that prevents me from saying words that start with th without thinking very clearly and hard about the whole situation.
hmm.
Hell, Ember, it's good to see you. Um, I'm glad Ember's here. I'm glad Ember's here. I know Ember was gonna show people the Cross Bronx Expressway, and all he was able to show us is bumper to bumper traffic. So this is an interesting thing that I thought of just as we came here, because we're going to talk about photons.
You
And
want to talk about
photons are,
photons? Let's talk about photons.
we're going to talk about photons. But one of the things I thought of is like, I do a lot of open deck work. So like I have to take photons with me everywhere I go. But Ember does a lot of closed box work. And once he closes the door, there must be photons in there to bounce around. But is there a point at which those photons will just disappear and
Yeah,
expire, and then there won't be there anymore? And then by that very situation, Ember's loads are like necessarily lighter than mine, not just because I'm a heavy hauler and he's more of a traditional trucker. But like if we had the same product in each, on mine on the trailer and his in the trailer,
I have
is
no
mine
idea.
heavier because the photons are with it on the trailer, and his, like, the photons are outside the trailer? How would we scale that?
I don't even know what you're talking about, so I have
I'm
no
trying,
idea.
I remember I asked you last weekend which would weigh more, a pail of shadow or a pail of light?
Well, a pale light would, I guess.
Would weigh more than a pail of
Yeah,
shadow?
yeah,
Yeah.
because of E equals
Okay.
MC squared, right?
Yeah, equals MC squared. Yeah, that's right.
Yeah.
Because if you just have shadow, there's no C. You can't square the
Hmm.
C, right? So you just have E equals M, right?
Yeah.
So a pail of light weighs more, exponentially more.
Yeah. Well, so you have, so light has, a photon has a certain amount of energy, and the
Yeah.
energy of a single photon is related. It's directly proportional to its frequency, and the proportionality constant is Planck's constant, and
Okay.
so Planck's constant is a really, really, really small number. It's something like 6 point something times 10 to the negative 34 in units of joules times seconds, or which is all, I don't, yeah, that's the one that I remember that it's in, because that's units of action. You can express it in different units. You can express it
All
in
right.
the base units. But
And
that means that if that means that if you have a lot of photons, then you have a certain amount of energy, and energy equals mass times the speed of light squared. So then you can, divide by c squared, and you'll get a certain amount of like mass that you would measure. And
yes.
this is actually really, really, this has been measured in certain sort of senses, in some pretty neat experiments. There's an experiment in Florida somewhere. I can't remember which university off the top of my head, but they have an ion trap. So they have like a single ion, a single negative or positively charged atom of some particular type, and it those atoms can exist in different energy levels, and the way you increase the energy level, and the way that you make the atom go to a higher energy state, is that it absorbs a photon. And so when the atom absorbs a photon, it's got a little bit more energy, and that means that it should be like a little bit heavier, right? And it
Yes.
turns out that in some of these traps, you can trap an ion, and you can watch this one ion just like oscillate back and forth in this trap for months.
Wow.
Months.
But
And it
it
goes
does, the
around,
ion, it will eventually run out of its the initial energy is have it overcome by something, or no?
no, not really. I
Okay.
guess there should be at some level, because the charge has to accelerate, and accelerating charges emit things, but I don't know how that works. But I know that they can watch, like, the ion will emit, a photon or something, and it'll go and be in a different energy state,
Okay.
and then it'll oscillate at a different frequency, and that you can think of this thing as being like a mass on a spring, and the oscillation frequency is set by the stiffness of the spring and also by the mass of the object. So
Yeah.
you can see that the atom, depending on what energy level internally that it's in, depending on the arrangement of all of the electrons and stuff going around it, the atom is actually a different mass. And that mass is, it's because when you get down to these sort of levels and you actually think about the quantum mechanics of it all, it the line between energy and mass becomes fuzzy, and it's really cool. And Ember's exactly right. You can shine light on this thing, and it'll send up, it'll go up to an excited state, and then it'll decay back down to the initial state, and it'll emit that photon in a random direction.
Okay.
But only you can only go from certain states to certain other states. Otherwise,
it's like there's shells that hold them. You can't be in between.
Yeah, you can't be in between. That's sort of the quantum part.
You can't have them go somewhere. Yeah. They'll settle in an upper or a lower state, but not in an in-between state.
Yeah, exactly. So
we have a whiteboard.
Yeah, so,
anybody's playing bingo at home, whiteboard has come out.
Yeah. So you'll have like a
set up for this.
We have like different energy levels, okay? So the vertical axis here is going to be energy, and the horizontal axis doesn't mean anything. It doesn't mean anything here.
All right.
And so this would be
the
like
Z axis.
Like
we're not thinking in 3D. Yeah, the 3D.
No.
This is single dimensional.
Yeah.
This is the Weezel's easel.
Yeah. So you would have a ground state, and this ground state is going to correspond to some particular arrangement of the electrons, which have their own little spins, and they're zooming around in sort of weird ways and all that fun stuff. And then you'll have different excited states, and some of these excited states, and I'm literally just putting them kind of wherever, because that's what we do.
Like Super Mario layout, right?
Yeah. And so, for example, at work, we typically think of there being a state here, and then there being, because the atoms that we work with at work are strontium atoms, and we have a state here, which is our sort of main excited state. And if you want to use a photon to go from G to E1, I'm going to call it, then this photon needs to have a wavelength, lambda, equal to 461 nanometers.
Okay.
Whereas to go from here to here, you need a photon that has 698 nanometers. And then to go to this one, it needs to have 689. Man, I can't do both. Which is really annoying, because it's 689 and 698. And then
that is annoying. It actually looks like you wrote, I don't know, 689 and 698. They're 10 nanometers apart, but it looks right next to the bottom lambda. It actually looks like an 8 or a 9 to me, but I think you said a 6. And I think it's just because of the fuzziness of it. Yeah, okay.
It's the equal sign.
For the people that are writing the exam at the end of this stream, I want them to not make mistakes.
Yeah. But the thing is, this transition in strontium 88.
Yes.
This transition, the 698 nanometer transition, is completely forbidden. You can't do that with a single photon. Because
698 cannot be done.
Yeah, you cannot.
When you say forbidden, it's not against the rules at the.
It's against the mathematical rules. It's not against the rules at work.
Yeah. It's not like your boss said, "Don't you ever do this, or you'll get written up." And a verbal
warning. Actually,
physics won't allow it to happen.
Yeah, exactly.
Is that what you're saying? Okay.
Yeah.
Because this is
And
an
so
important distinction.
this transition is dipole forbidden, and it's also forbidden at like several other levels of quantum theory, whereas this transition is super allowed. Like these two, if you have your atom in an excited state, its lifetime up here, the lifetime of this state is 5 nanoseconds. Okay, 5 nanoseconds is how long it lives up there. If you have it in this state here, it is 21 microseconds. And if instead of using strontium-88, you use strontium-87, you can have this transition. Then this becomes allowed, but only at like third order or something. And if you put an atom in that state, if you put an atom in this state, it will last there on average, I want to say like 20 minutes. I can't remember actually.
Okay, but there is a period of time it will stay in that state after hitting it with a wavelength, but you're saying it has to be an isotope of strontium.
Yeah,
that's
it has to
different
be.
than,
It has to be 87.
It has to be the 87 isotope. So, can you remind all of us, and mostly me? I know strontium is commonly used in many physics experiments, but are those isotopes of strontium radioactive in a dangerous way? Like, is this done in a, or is
not that I know of?
Okay.
No. The only radioactive element I've worked with has been potassium 40. And potassium 40 has a half-life of like 1 billion years or something.
1 billion years. That's a long time to wait.
Yeah, it's a long time. So you don't. Yeah, it's not something we worry about. The more annoying thing about it's annoying that it's radioactive at all, because at least for us, because that means that there's not a lot of it around. It's not the most common isotope,
because you need it to decay into that isotope.
Yeah, from something else. Yeah,
and you've only had. I mean, if you do the math, like if we took 14 billion years of like the entire universe being around, and then knock off like all the time in which there was no strontium at all, because no particles had gotten to the point where that could happen, and then we would we've maybe only had in these half-lives, like there's maybe only been like 10 chances to get that decay. And then you need to have a whole bunch of it trying to get to that point.
Yeah. And I mean, it can decay at any time, because it's, that's how half-lives work. It's not like a little clock inside of it that says, okay, now you're going to decay. You could have one of these excited states. It could live for 5 minutes. It won't. It won't. Because
it's physically possible. It will not happen.
Like because the half-life of it, I guess, is probably around like 3 nanoseconds, because we use, instead of using half-lives, we use like the 1 over e decay time, because you'll have some population of atoms, and if this is time and this is the number, then it goes like that, right?
Yeah.
And so half-life is when this decreases by half on average, but we generally go when it decreases by a factor of like 1 over e instead, which, is pretty close, because e is 1.718. No. 2.71. Yes, 2.718. It's not 1.718.
I mean, you're close. It's close to a half, but it isn't a half.
Yeah. But that doesn't really matter so much. But all of these different energy levels, this is the quantum part of quantum mechanics. The fact that the atom can only exist in energy levels like this, or like this, or like
And one
these.
G, is it one G and one E? Am I remembering that right?
Uh,
But,
G, E, and I'm just labeling them however I want.
yeah, but
The actual ones was like this is
G is like it's unexcited, unhit state, right? Like it's ground state is the one at the bottom, is the one
yes,
it just rests in. And then
yeah,
one E is an
uh-huh,
excited state. And
yes, yes,
the three bars that you show, the shelves say, we'll call it,
uh-huh.
can we call them shelves? So when you get the electrons to those excited states, it can settle in any of those three, but strontium 88 will settle only in the upper one, and the
It'll
lower
no,
one, no or no.
no,
Okay.
no,
No, because you said
because
it couldn't
it
do you couldn't do the bottom
you
one.
can't do it directly. You can't do it with one photon. You can't do it with one photon. You can't go from here to here with one photon. You're not allowed to do that. But when you go up here, which you can do with one photon, from here, this thing can decay. What are all the states that it can decay to? I'm gonna pull up the wiki on my thing because my brain just like normally stops working on Saturdays, and I don't want to, while I'm being recorded and live, I don't want to make a
Did I not,
mistake.
Vanny, did I not tell you to take the pickle jar to work and bring some strontium 87 back home in the pickle jar?
I don't think you did. I don't remember you saying
Oh,
that.
okay. Because like I told you, you got to work and poured out all the photons. You could fit some strontium in there.
Okay.
You'd only need to bring the electrons in the excited state back to show us. You could leave all the rest of it there. And
Okay.
electrons on their own take up less room. Okay, so now we're gonna share you.
Yeah.
Adding to stage. Okay, does this layout work for people? Ember has a question, which is a big question, but like, and I assume he means like the excited states and what triggers it.
Like
But
what changes from one moment to the other that causes the decay to happen at that moment? If that is the question, nothing.
okay,
Nothing does that. It is an uncaused event
but
in that sense.
we do know that 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 certain elements decay, especially certain isotopes of elements don't want to be stable and they do decay. Even if it's super slow, they do decay. But you're saying there isn't a catalyzer of that. There isn't something that is introduced. There isn't a level of heat or light or
Yeah,
anything that causes that to be a chain of events that happens. It just happens.
it just happens. It
Okay.
happens for reasons. It's not uncaused or unexplained in that sense, but
Okay.
there is nothing temporally that is sort of different as
Okay.
far as we know. What explains it, what causes it, is the fact that the energy levels are coupled in some way, and they're coupled to the fact that they can release a photon. So you can have the or it can release an alpha particle or a beta particle or whatever. So you have your quantum state before the thing decays, and then you also have a quantum state where you have one decay product, another decay product, and they're moving away from as away from each other. And both of those are quantum states, and they will be connected somewhat if it's allowed. And how strongly those states are connected is sort of how easy it is to go between them. And so in this diagram, we
Okay.
have the 1s0 state here. This is the
Okay.
ground state of
Yeah.
the strontium atom, and it is coupled very, very strongly to the 1p1 state here. Uh, and what that means is that if you have an atom up here, this atom will only stick around for about 5 nanoseconds before it decays. And it almost
Okay.
always decays to this state because those two states are connected sort of pretty well. their wave functions sort of overlap. If you have an electric field, then you have and like you can think of it as it's moving, it's wiggling your wave function around, and if it wiggles it into the wave function that corresponds to a different state, then it will absorb the photon, and now the wave function, the electron sort of motion, will be wiggling in a different way. The electron can only be wiggling around the atom in particular ways. And this chart here shows like all of the sort of different levels, or not all of them, not all of them, but a lot of them, of the different levels. And it's very easy to connect, or for an electron to just wiggle its way out. Like if an electron is in this 1p1 state, this one right here,
yeah,
that electron will sort of, just by moving around kind of on its own, it's going to throw off a photon. And it's really easy to do that because it's easy to throw off a photon sort of in a way that makes it wiggle like it does in the ground state.
Okay.
And but you might notice that there's this other line here, this really faint line.
Yeah, it's connecting to this other shelf.
Yeah.
If you will.
And also notice how these
they're double arrows moving.
Yeah,
it's moving back
they should
forth.
all be double arrows. They should all be double arrows for the record. There's,
okay.
The ones that aren't, there's not I don't know if there's a reason for that.
There's no reason because this is like a what goes up can come down kind of thing.
Yeah, exactly. There's the thing is it's a symmetric interaction. So
yeah, so if it goes up, it will come down to this other state, and the question seems to be about the duration of its time in the excited state, but also what it does when there, or what it does going to and from, and then also it sounds like I don't want to speed you up into the thing you were about to say, but it sounds like you're saying sometimes the movement can go from one shelf to the other instead of back to its initial ground state. Is that what you're about to say? Okay.
Yes.
All right. I'm not trying to jump ahead. I'm not trying to jump ahead.
That's exactly where I was going.
I do want to say that Dog wants to get rid of wiggle and put in glide. And I want you to do that. Is that no, that is not the diagram for folding origami cranes. Hello, Maya. And hello, Mikey, and hello, Dog, and I can't remember who else has come in, but welcome everybody. I appreciate everybody showing up here. So what I was thinking is when you explain this, you could maybe say what I want to know, because it seems like when you were shaking your hand around, and I know there isn't a good diagram on a whiteboard for that, you're talking about what the motion of the electron is in the excited state, at the excited state, as opposed to like while it's there on the shelf, say, not what it does in between the G state and the, is that 5p state?
Yeah,
I can't read the labels that well.
Yeah, because they're kind of small. This is the bottom state we call the 1s0 state because we omit the other ones on, because all of the states that I deal with, all of the states that I actually think about and deal with and like need to know like the numbers of is just this one here, this one here, and then these three here. Even though we have three lines here that are also strong. They're thick lines. Because if the atom is there, then you can use one photon very easily to get up into the state, which is a 6s state. I couldn't have told you that. I mean, I probably could have figured it out because the thing, but there are three sort of p states here that, and one of them you can connect to directly from the ground state for if you're in strontium 88 or any isotope of strontium. The bottom one, you can only do it with a single photon if you're using that particular isotope of strontium, because the nucleus has some spin, which breaks some like symmetry, basically.
Okay.
And then the top state you can't go to directly because The 0 in this state here, the 1s0, that's the spin, and up there you would have a 3p2, and you can't change your spin of your electron by 2 using one photon, because photons only have one spin.
Yeah.
But when the atoms are up in this state, most of the time they can decay back down here. So if you shine a laser that is 461 nanometers, a blue laser, on the atoms, they will absorb a photon and then release a photon really fast, millions of times a second, if you have just a little bit of laser power. But 1 out of 50,000 times, they don't fall back to the ground state. They fall to this state. And then that state decays to these states over here.
Okay,
and
so it's like because you're talking about out of millions. So
yes.
This 1 every 50,000, by having it happen so many times, and the fact that it will do it so many times in such a short space of time, this 1 in 50,000 isn't. It's statistically relevant, but you're overcoming that by doing it a lot.
Yeah, if you just have a million atoms and you're shining the laser on them, and you have a laser power of like 1 milliwatt, like a small amount of laser power, you're going to immediately have all of your atoms pumped within a few milliseconds. All of your atoms are going to get pumped to this top state here, where this arrow is being pointed at, the 3p2 state. And those atoms are just going to sit there because they can't decay. They can't go down to this one because there's no way for those electrons to throw off a single photon. They'd have to throw off 2 photons at once, and that's way, way, way less likely to happen.
Okay.
So when we shine the lasers onto things, eventually they'll end up in this 3p2 state, and suddenly they're invisible. We can't control them with this laser anymore because they aren't in one of these 2 states. What? I'm trying to parse that, and I can't.
Which one? This one? This one here? I mean, I can usually see it, but my pareidolia isn't working today. But yeah, and I also want to put this up here because Ember and I are drivers. I can't remember how many other drivers there are here, but I know Ember and I drive. So yeah, no, I can't follow this one. The crane I almost got because I see kind of like a wing, and I see kind of like, I can see how like you could take the lines up on the right hand side as like maybe like the neck and head of a bird type thing.
Yeah, but I have no idea.
I can't get the diagram slot. I can't figure that one out. But anyway, I'm taking that one down because I didn't put it up right away because I wasn't sure what to do with it. But I was like, you know what? I mean, I think it's funny.
Yeah.
It's funny because this diagram is permitting all sorts of things. What I think what's interesting here to me, and the question I was asking, I know you're getting to it, Dr. Tap. I just want to restate the question because the conversation you and I had about this via text was not no one else is privy to that conversation. So I'm just gonna and most of that conversation I won't bring out in the open because I mean nobody needs to know about our private subatomic particle conversations. But what I was asking was about how I grok, which is a word I learned from you, about how I intuit what happens. And so my question was really and I can see how you're getting this. My question was really like, when you add photons to something that have energy and you're exciting them, which is what I get it. Like that's what I always think of energy. As you add energy to a system, that you're likely moving things more, and moving things more tends to result in more heat, more more light, more whatever, and things are emitted from that. And I guess like my question is, because when I think of all the things that I know to do mechanically to move heat from one place to another, they generally don't actually take heat away from the thing. They displace heat to somewhere else.
Yeah, and that's
Right?
generically
So
true. You're always
okay.
just displacing heat to somewhere else. Your question is, how do you use lasers to cool things down?
That's right. So how is it by adding energy to something? Like, because you talk about aiming it at it.
Mm-hmm.
Okay. When
Yeah.
you're aiming energy at something and you add energy to it and it comes out colder, and not just a little bit colder. And I don't know what strontium's original temperature state is
It's
in your
a real
lab.
thing.
It's
I
what's that?
it's room
Let-
room temperature, but then we heat
No,
it
it's
up in
room.
an
Okay.
oven, so it's 430 degrees Celsius
Celsius in
in the
it's
oven.
above room. It's above room temperature. We're not talking
Yeah,
Kelvin.
because otherwise it'll just stick
Yeah.
to the wall.
Okay.
So
This is
you have
okay.
an you have an atom,
Yep.
okay, and say the atom is at
Hold on.
rest.
I'm changing. Hold on. I'm changing. No, not that.
Yeah,
Is this good enough, or should I make you like this and make
I don't
you?
care, whichever you
That's
want.
gonna remove you. I'm gonna do you like this. Here is this is good.
Yeah.
Okay, what's the blue line? Okay, I don't know. All right,
So if
they're talking about the naked stick diagram. So just ignore all that, please.
so if you have
Tell
the
us about your
atom,
potato.
this atom is at rest. It's not moving. Okay.
Yeah.
And
Yes.
then you hit it. You hit it with a photon. Okay.
Absolutely. Yep.
And then after that happens, that that is going to produce an atom which is moving in this direction
Okay.
because you've hit it with this thing.
Yep.
And the photon has a wavelength lambda. Okay.
Yes.
And it also has a momentum. We're going to call it P.
Yep.
The photon has a momentum P, and that momentum is equal to Planck's constant divided by lambda. So
Okay.
conservation of momentum means that if this thing is here and it's at V equals 0, and then it absorbs a photon, plus 1 photon,
Yeah.
and now it's at V greater than 0. Okay?
Okay. Yeah.
But what if we'll call it V V equals 0 plus 1 photon, now V equals 1.
Okay.
In that direction.
Yeah.
Okay? But
Yeah.
what if the atom was initially moving this direction with V
Okay.
equals -1? And now you add a photon. And now at the end, V equals 0.
Yeah, because
So
you don't know the inertial reference of
we,
each thing. Like you know what you're putting in terms of in phase wavelengths of light, and you know how to set them. That's
yeah.
why you're using a
Well,
laser
yeah,
that you can calibrate. But the atoms
the atoms,
necessarily are somewhere, right?
yeah, they're somewhere and they're moving in some direction. And the atom will only absorb the photon if the energy of that photon
How do I switch us?
is equal to it'll only absorb a photon if the energy of the photon is one of those lines, basically.
Okay.
And if the atom is moving towards the laser, then you get a Doppler effect.
Yeah. Okay.
It's moving towards it, and imagine the atom is moving towards this laser at half the speed of light.
Yeah. See, like, yeah. Okay, I get it. Yeah.
Then it's going to be seeing like these it's going to be seeing the oscillating electric field. Instead of being like this, it's going to see it.
It's actually shortening
like
the wavelength because
it becomes
it's coming towards us. So like the redshift, blue shift that we talk about, even in like sound waves and things like that, where we try to like explain like the change of frequency that you get from like approaching or going away from a sound wave that is the same wavelength the whole time, but its movement towards or away from you changes the frequency at which you hear it. And then actually the atom experiences this in phase, like, because an in phase laser a laser is in phase wavelengths that are all set the same or very close to the same.
Yes.
And so I tried to do a small amount of research so that you wouldn't be just talking to a trucker, but you'd be talking to a trucker that read one wiki article, and which should improve the situation. But yeah, no, so this makes sense. So the atom experiences it has a different experience because of its movement.
Yeah. Exactly.
And then and then inertia of some sort is involved here, but what we grok from Newtonian physics doesn't necessarily apply because this is quantum physics, and so that's where we need big brain Vandy to explain it all to us.
Okay, so I'm going to show you 3 sort of examples. That's V equals 0.
I had it just switch them.
And
this one
is
this one
V minus 1.
This one. How can I switch this?
I don't know.
Spotlight layout. Can I do that? There we go. That's what I was trying to do. Okay, thanks, Mikey. Mikey's been trying to coach me. Is this okay, Mikey? Please type a 7 for yes. Okay. Sorry, Mikey's been trying to coach me in the side chat, and I've been not getting it. Yes, okay. I feel like I'm in physics class again.
So, here's what we've got. In the lab frame, on average, the atoms aren't moving because, it's the lab frame. Everything's on average stationary. And you have your laser. If you were to like take a thing and measure the frequency of the laser, you would measure it, and it would be, for example, it would be like 461 nanometers. But if your atom is going towards the laser, same laser, same photon, but now we're looking at it from this atom's perspective, and it sees a shorter wavelength. It sees a 460 nanometer photon. These are obviously dramatically like crazy enhanced.
Yeah, you're making sure people can see this on a teeny tiny little screen, because some people are watching this on an iPhone 3.
Yeah. And if the atom is moving away from the source of the laser, because the laser is always going in that direction, okay?
Okay.
If it's moving away from the laser, then it might see it at like 462, okay?
Mm-hmm.
And so you got 462, 461.
And for anybody that wants to ask this question, the amplitude is not to scale.
No. Nothing.
The iPod Shuffle Mini. I remember those little iPod. I had an iPod Shuffle. I don't know where it came from. I think my wife won it and let me borrow it for like going to the gym years ago.
Yeah.
I don't know where it went, but then it just had a button pusher, so you just play music on it. You had to set up your playlist before you left home. But then people had a video one, and it was about the size of a postage stamp, the video screen.
Huh. Wow.
Yeah.
Yeah. Like the watches nowadays.
And I think Mikey's making a reference to that, I think. I'm pretty sure. I don't know about this 0.6 part, but What does v equal? That's the
V
velocity.
is velocity.
We're talking about
V is
velocity in
velocity.
reference to
Yeah.
each one. The zero is a zero velocity atom, one that is not moving.
Yes.
In this example, the
Yes.
one that's +1 is moving. Like, well, I'm going to use cardinal points. I'm just going to say that the red atom. These are all the same isotope. These are all the same isotope of strontium atom for this purpose, for your description. Is that correct? Okay. So all the same. I'm explaining it because I'm the trucker, not the physicist. And so moving to the west at a speed of one unit more than 0 is the red one. Moving not at all at a speed of 0 is the green one, staying put. And moving the exact same speed in the opposite direction, moving due east, is the blue one. Is that blue or black? It's blue, right? And if you're colorblind, I'll help you sign a petition to get your pilot's license anyway. There's no need to exclude this.
So and it's also represented by the little arrow on here.
Yeah.
Because the in all of these cases, the photon is moving east. In all cases, the photon is moving east compared to the lab frame, compared to the guy standing there working at the computer. But in this one, the atom is moving east as well, and so the photon looks more red. And in the bottom one, the atom is moving west, and the photon looks more blue. But if you go back to the diagram,
that would be. I don't want to remove. I want a full screen layout like this.
Yeah, you'll notice that this right here, it's 461. Okay, the atom is not going to absorb a photon that it thinks is 462 nanometers, and it's not going to absorb one that's 460 nanometers. So what we can do then is we can change the frequency of the light in the laboratory in our normal rest frame. And so I'll just make the light coming out of the laser in the lab frame 462. Okay? You probably want to go back to me on the thing.
Okay, yeah, I gotta go. Sorry.
Yes, they are. They're in nanometers.
Okay.
All of these are in nanometers.
Is that good?
So if your laser in the lab is at 462, then that means that the atoms going west, they see light at 461. And the atoms that are going east, they see light at 463. But the resonance value, the only one that they're going to absorb is the stuff going at 461. So that means that only atoms which are moving against the laser are going to absorb the atom. And the photon has momentum. So after it absorbs this atom, if it's going really fast this way, if it was going really fast this way beforehand, afterwards it's going a little bit less fast this way.
Yeah.
And then later it's going very slow. And now it starts to see this as maybe 460.5, and it stops absorbing them as much.
Okay.
Because it will only absorb them. The probability of absorbing them, I'm going to draw a little box off to the side here because I don't want to erase the rest of it. So the probability P stands for probability, F stands for frequency, and we're going to have a peak like that. And so
Okay.
this is 461. Okay, this is actually in wavelength. Okay, what wavelength? This is wavelength in nanometers.
Yeah. Yeah. Yeah.
And so this is 461, and this is 462, and this is 460. It's only going to absorb photons when it's close enough to 461. For the
Okay.
record, again, these are also like you have to be way closer than one nanometer. You have to be like fractionally accurate to within like a part in a billion or something. I can't remember. But that means
you've got that volume knob attached to your laser so that you can make those adjustments. You're using numbers that are like a full integer apart in order to help us understand a concept.
Exactly. Yeah.
Right, okay.
Yeah. And so they will only absorb atoms when they're in a certain distance, and they're always going to absorb the atom and get pushed back in the direction that the laser was going. They're always going to absorb the photon and be pushed by the photon in the direction of the laser, but eventually they're no longer moving fast enough, and now they sort of see it over here and they stop absorbing it. What this means is that if you had a bunch of atoms going in random directions and then you shine this laser on it, after just a short moment, you're going to have kicked this thing with one photon's worth of momentum a whole bunch of times, and now none of your atoms are going this way anymore. Because you basically you kick them until they slow down enough that you're not like seeing them anymore, and now now all of these atoms have become green.
So you've actually imparted a new value to their movement by hitting them.
Yes.
Or you've got them all in the same. You've got them all like it almost seems like you've combed them all in one direction.
Yes, exactly.
Okay.
But so what happens then if you take this same laser and you take half of the power, and if you were to take half of the power and you put it through a little cable or something, and now that laser is coming also from this way. It's coming from both directions. So now,
okay, so can you slow down for a second, because this may or may not have created, because you said through a cable. Like,
oh yeah, you could use a mirror. You could use whatever.
So and let's not revisit the two-way speed of light problem again. But let's talk about this for a second. So when you have power, nothing has changed to amplitude, wavelength, frequency. It's intensity only.
Yeah, but yes, but now it's coming from two directions.
Are you shooting it? You're physically changing it to have that same laser split its intensity into two and shoot at the atoms from two directions. You're physically shooting like this, right?
Yes.
This is happening simultaneously.
Yes. And then we do that. We do that along this axis, and then we also do it along this axis.
Okay.
And then we also do it along this axis.
So the Z, the Y, and the X have now been activated.
Yeah. And so now this atom is at rest. It sees this one and this one at 462. But this atom is moving this way. So this same laser, it now sees at 400, move this back to being 461. Now it sees this as being 461. And this one, which is moving this way, 461, it sees that one as being 463. So guess what? This atom is only going to absorb from that laser.
Okay.
This atom is still, it's not going to absorb anything. It's already motionless.
Okay.
Motionless means cold.
Yeah.
And
Okay.
this atom is only going to absorb from that one. Okay,
Gosh.
so
Okay.
that means that after a moment, this one will become green, and also this one will become green. And now all three of our atoms have stopped moving because
Yeah.
we
So
shined
you've
a laser on them.
so in this so when we talk about something approaching 0 Kelvin, and absolute zero is another word for that.
Mm-hmm.
I'm sure everyone remembers from OAC physics, and when we talk about that, actually probably nobody else went to school in Ontario, but not in the era I did. But when we talk about absolute zero, um, there's and I know that there's some newer research than when I went to school that gets into this, but the idea being that at absolute zero, a particle of any type, but let's talk about atoms because that's the example you work with and the one we're talking about, would go from an excited state of any kind, not necessarily like an excited state where electrons are like blowing off of it or whatever, but just that there's always a bit of vibration in a piece of matter. And so we take a
Yeah,
single atom, there's a vibration to it. That motion that you talk about is kind of akin to the way we were taught in school to think of it as like everything vibrates. And so at absolute zero, everything would come to an absolute stop. And that you
yeah,
could like because not there's no the vibration would disappear completely. There would be zero vibration.
yeah,
No vibration at all of any kind.
yeah.
And when you described this, I think you actually were talking about this somewhere else. Just conversationally, you said you'd had it to within a very tiny fraction of absolute zero.
Yeah,
And
the coldest I've ever measured is 12 billionths of a Kelvin
12 billionths of a Kelvin,
that I've measured.
which
And I've
is,
produced colder. I've produced colder. I just
it's
can't measure
produced
colder.
colder. That's the coldest you've measured with the
Yeah,
equipment you
because
have to measure with. And
yeah, because
you've
yeah.
gotten it. So in this case, when we talk about a 0 degree Kelvin, not 0 degree, when you talk about 0 Kelvin, degrees are used for Celsiuses and Fahrenheits and whatever. Fahrenheits, Fahrenheit, whatever
I
that other
like
weird one is.
Fahrenheit, so I'm going to use that one.
Fahrenheits. Yeah. I may have coined a new word, and I may have insulted an entire country. But don't worry, they're my next door neighbors, and they're super cool. So
Yeah, plus, we're rich and powerful. We can deal with it.
that's right. You're rich and powerful, so you can handle it.
Yeah.
Yeah. Well, some of you are. Some of you are. Unfortunately, some of you aren't. But we can have another stream about that at a different time. Um. All right. So it sounds like if like my grokking now kicks into gear again, and now I'm understanding that you are using your focused beams of light, these lasers that are set to a specific wavelength,
Hmm.
knowing what reactions you get from the strontium atoms, you know
Hmm.
that if you hit them with a enough of these photons at these specific wavelengths, and you hit
Hmm.
them to get them all combed in one direction and then hit them again from multiple directions, that you can actually get it so that on average they get to a point of stillness that is not usually experienced in the rest of the world. And so by adding these photons in this exact way, that like, and the word resonance was used earlier, and that's a great word because when things resonate, they
Hmm.
tend to pick up something that they want to have. Like when you pluck a string that's in tune, you get a resonance, right? And you get like a resonance chamber in like a guitar, for instance, is curved because it then allows you. There is always a piece of air that can resonate with the note of the string that you've plucked inside of it, because you have two curved surfaces meeting each other. So that means there's always a piece of air that can do that. And I hate to come back to sound, because sound and light isn't the same. But I think we're better able as humans to grok sound waves than we are light waves.
Sure. Yeah.
Because, and I think that's why, and this is going to be one of my tangents, which I will come back to the same thing I'm saying. One of the reasons why early physics of the last century were caught up in the idea that there's an aether through which light would move, right?
Yeah.
Because their understanding of wave patterns and how they moved was through media. And when you remove the medium, sound would stop. And so if light doesn't stop, then surely it must move through something. And that something must be akin
if it's a
to
wave.
If it's a wave.
Yeah.
But I think light's more complicated than that. But I think this is really interesting. Oh yeah. Commanders mentioning they're having a spooky movie night, which I'm not sure if I can join or not, because I think my wife and I are we're going back to doing some stuff together. But I got her to let me come and play with my friends on the internet for a bit. Dog is wrong, but you can. What Dog's talking about is actually something else. It's not blocking sound waves. It's mixing them up with stuff so that by adding sound waves, you take away intelligibility. And that's a whole different thing. And I've put in lots of white noise cans in places to help where you can't stop sound waves from traveling. You can make intelligibility disappear so that you can maintain privacy, which is oftentimes for some places more important.
Yeah.
So
that's what they do. That like
is it? I believe they call it interference pattern, or is that the right word for it?
I mean, I think it's just making a louder noise so people can't hear you.
Yeah,
interference would be like noise canceling headphones. They intentionally make noise that will cancel out.
Okay,
but that's all.
So like I'm now at the point where I'm grokking where you're going with this. You might not be done, but I'm starting to grok what's going on.
This is basically how lasers
block on. So
cool down
okay.
atoms. Yeah. I mean, this right here, this is how laser cooling works. The main type. There's other types, but this is the big one. This is the workhorse. And this atoms that are moving, they have to be moving already, like kind of, because if they're moving really, really, really fast, then you're only gonna only a tiny little sliver of them are gonna be seen. But you tune your laser so that in the laboratory it's a little bit more red. It's a little bit red of the transition.
Okay.
And that means that atoms will only absorb the light if they are blue shifted, which means if they're going that way, they experience a force that way. And if they're going that way, they experience a force that way. And if they're not moving, then they don't experience any force, and you have to do another thing, because then they'll start to fall. And they're not going to fall fast enough for the laser to block them.
Yeah, no, I'm seeing some very I'm seeing what's going on here, because you've drawn it as these little potatoes with arrows, makes me understand much better what's going on. It reminds me of what I'm now seeing where my brain went wrong. And do you remember I sent you a video a couple of months ago of a guy that also does a laser experiment?
I have no idea.
He takes a single atom and he puts it on a little stick and he shines a laser at it. And what he's trying to do is take images of atoms and electrons. And so he shines his laser through a very small, thin thing and tries to capture one one atom. He tries to capture the shadow of that atom on like a film, the way a camera would measure it, like the way we would take a
That's
picture. Because does that make sense at all to what like? And I don't know
yeah.
if you even had a chance to go and watch it. Go ahead.
That's how we do it. By the way, that's how we take
Okay.
images. That's so if you shine light on atoms, they will emit the photons, and you can just collect those with the camera. But you can also shine a laser on the atoms and then look at the shadow, and that's actually better in a lot of ways because
Cool.
you can be a lot more precise and stuff and accurate.
Yeah, I know, and I find it amazing. And so I think when you talk about doing this, you explained that you have like, quite a large number. I think you said at least millions of atoms. Maybe it was
Oh
more.
yeah.
Yeah.
I mean,
So,
in the early stages, we have billions and trillions because we have a chunk of
yeah.
strontium that we're like heating up with like an oven, and its atoms are just coming off of it.
Yeah, so the oven is getting the atoms to come apart from a molecular state.
Yeah,
And,
from
and
a
so the
metal
heat
state, more like from like a metal state.
from metal state.
It's
Okay.
like literally like it's a chunk of strontium metal because strontium
Okay,
is a
yeah.
metal.
So now when they're arranged like a metal, like I'm probably using wrong terminology, and maybe we should clarify this, because if I don't know it, maybe other people don't know it, because truck drivers tend to be exceedingly well educated in the sciences. So I think I used the word molecular in that when I think of a metal, even if it's all a pure element, I think of it as like they've bonded to each other.
I also totally think that metals count as molecules. I agree with you. It's an unpopular opinion, but yes, I agree.
I don't want to but I don't want to fuck up terminology, because terminology is important, and precision and terminology is important, particularly in sciences, because when we use a language and we're precise, even if we're using jargonese, no matter what industry we're in, that jargonese can confuse a layperson or someone uneducated in that or unexperienced, but it allows for quick and precise and correct work done amongst people that are educated, right? So if I if I tell you I'm gonna go get a 470 hoe and I'm gonna put it on the deck and I'm gonna set it with one shim, many people here may have no idea what that is. Dr. Top, I'm assuming you know just from osmosis from talking to me several times.
I know what the word shim means.
Well, that's pretty good. So but if I was to get that information from my dispatcher to make sure that I have things set correctly, they would have really quickly told me what I was doing, how I was going to do it, and then I could go then measure to make sure that I could safely transport through an area, because the height of the thing with that setup should work. And I can go measure it, make sure it's true. But if they and in this case the shim holds things in a certain position for traveling down the road, and there is some up and down because these things ride on airbags. So we do allow for that, and our level of precision and measurement is like, we want at least half an inch, or say like a centimeter of play. So if I measure that something's going to fit, I measure that it fits. Plus, I have a full centimeter at my highest point of extra room, because I don't want to bounce a little bit going over like something, and then the measurements given to us by the people that have put the measurements on have also given a couple of centimeters as well, because they've allowed for snow and ice buildup, water buildup, which actually can raise a truck up off the ground by a small amount. But a small amount is a lot if you hit doing 100 kilometers an hour with 50 tons of steel strapped to another 50 tons of steel, and you hit concrete and you're a centimeter out, you're going to do some freaking damage.
So water raising the height of your load, is that because the layer of water on the road has a certain amount of thickness?
Yes, it would actually, your vehicle could actually be taller. The other thing that the water could do is it could cool down your tires a little bit because it would absorb more. The road would be colder and your tires
Mm-hmm.
would be colder, which might help you in a way because your tires are
Yeah.
shrinking, right?
Yeah.
But
Yeah.
there's a lot of things at play. So the thing is, we wouldn't talk in terms of like, um, you know, quantum quantum measurements that you use in atoms. We're talking in pretty large distances into which you could fit trillions of subatomic particles and the space
Yeah.
between them, right? But our margins of error are large. And to bring that up doesn't do anything for this conversation other than to say that
Well,
if you're precise in your industry and I'm precise in my industry, the people communicating are doing so quickly, efficiently, and clearly.
yeah.
And that's
I
why
would
I
never have
like
thought.
to get into
I would. It would never have occurred to me that the layer of water, it has some thickness and raises up your truck a little bit. Like
it
it's
does a
clearly
little bit,
true,
a little bit.
but
It's not a lot, but it's a little
yeah,
bit.
but
And if you hit
it's enough that you need to know about it.
if you hit a concrete or a steel bridge with a big piece of steel and your overall weight is like, and I run relatively low weights and heavy hauling so far because I'm new at it. But I think I'd be running in like my higher weights would be over 170,000 pounds total gross weight of a vehicle. If you have that amount of weight moving at 100 kilometers an hour towards a relatively immovable object, and you make contact even with a half a centimeter, bad things are going to happen.
Yeah, I mean half a millimeter, bad things are going to happen.
Exactly. You
Probably.
don't need
Like
so
if it
so
doesn't fit, it doesn't fit.
that's right. It either fits or it doesn't. And
Yeah.
I moved one of my tallest loads ever yesterday morning. And I was given not just I knew what I was doing, I knew what I had. I ran things at the lowest possible setting. I was told ahead of time, this is what you're up against. Please do this. And I was also told, please call in. We're going to tell you exactly which roads to drive on. Because
Yeah.
there are roads upon which I can drive relatively unfettered,
Hmm.
and there are roads upon which I can drive and I might have a problem.
So
Right.
how often is that because of height limitations, and how often is it because the road is not strong enough to handle 175,000 pounds or whatever?
Uh Hi Bree. It is okay, so on the load I did yesterday, there were no weight considerations whatsoever. I had 7 axles holding up less than 20,000 pounds, which is nothing.
Oh,
One
yeah.
one single one of any of those axles, I could have had one single axle, any one of the axles on my truck, including the front axle, because my front axle is a 22,000 pound front axle. So I could have an essential like a unicycle to deliver this thing. With
Yeah.
any of the 8 axles I have to work with, every single one of them on its own could support the weight and do so legally in on any major highway in this province, and except in March and April where we have frost restrictions.
Yeah. But
Okay, so but just like in November, no problem, just not a problem. So but other days I'll move something and I'll have a special permit to take a crane somewhere because a longer, bigger thing won't work. And yeah, so Commander 401's pointing out something about the special permit. So that is totally right. Um and oh, you got okay, that's great, Commander. The Commander's got a couple of videos she, they are doing. I have no idea. Commander's never told me. I've never asked what gender they go with. That's a that's a really stupid thing. And I was trying to I'm trying to read too many people's names at the same time. I've always called Commander 401 they because they've never said, and I don't know. And they're kind of like a penguin in a spacesuit. So the commander can say or not. I don't care. It doesn't matter. Maximum of 80,000 pounds in America, and they are also a trucker, and that is right. And in Canada, it's not different by much. That you can do a little bit more. It's not so much that you can do more weight. It's just there's more things you can do without special permits because you can just add axles. in Canada, but almost everything I do is under special permit because almost every day when I go out, like some days it won't be like when I go out on Monday, I'm just doing straight freight. It won't matter because that's the work they have for me to do. But on these low deck things, it's special permit all the way because even my empty trailer absolutely has to. It has to be that way. So everything I do is under special permit because the company I work for specializes in this. And I have a book this thick in my above my head, like I have a binder, and each page of that binder is a permit to run in a different jurisdiction. And I have pretty much every corner of this province, a few places in Quebec that we go to often, and a few US states all covered by that. And then if we go over the limits that we paid for on general permit, we can then buy extra permits to do that. And that has been done. So yeah, so like 80,000 pounds is like, that's total gross on a truck. And I would say like multiple times in a week, I will pick up a single piece of equipment that weighs over 80,000 pounds as the payload. That's just what we do for a living there.
Yeah.
But knowing that stuff's important. Now, this is a bit of a tangent, but it's not that big of a tangent because precision in anything you do is important. And I know that, I don't know if Ember still does this. Ember has done refrigerated loads before, and they've talked about how they have to monitor the temperature, right? And sometimes you have to monitor humidity, and sometimes you're keeping stuff from freezing, sometimes you're keeping it from what am I saying? Yeah, you don't want it to thaw. You don't want frozen stuff to thaw out. You don't want cool stuff to freeze or get too warm, and you don't want warm stuff to get too cold. And you can also be monitoring for humidity for some things that can't get too dry or too wet, because they would go bad, depending on what you're moving. So that's another level of precision. Now, would it be as precise as the billionths of a degree that you're talking about? No, but you know, there's precision in everything. That's what's important. And I do want people to go check out is a reefer. Yeah, Ember, you're hauling reefer now, Ember, I think is what you're saying right now. Is that what that means? Can some of the young kids tell me it's RN? Because RN I thought was registered nurse, but
it's
right also now. Right now. Okay, thanks, thank you, young lad. Come here, young whippersnapper. Tell me, what does this mean?
What?
Yeah. So
somebody in chat asked if I have a portrait of spaghetti sauce on.
Yeah, I'd like to fucking know that too, because I don't know where they see that, but I want it. There we go.
It's this thing. It's been over there.
Okay.
And what it is, it's a joke. It's a joke because MOT stands for magneto optical trap. And this right here, this is a picture of one. At the middle, you've got lasers coming from all 6 directions. And it says fermionic goodness because potassium 40 is in bananas. And then at the bottom, it's got like the mass of it and stuff. And the reason it's red is because the lasers that you use to cool down potassium are red lasers. And so one of the undergrads in my last lab like made this and brought it into the lab. And then since I was the last student in that lab when everything got taken down, I got to keep it. So
yeah, that's cool. And Mott's is a brand of stuff, MOTTS, and that's
exactly,
that's the joke, right?
That's the whole joke, exactly. But it also stands for magneto optical trap.
What does it mean? Okay. And Commander is sharing interesting information. You know what? I remember Commander did share with me in another conversation that wasn't publicized. So I don't want to like I won't say too much about it, but peeps and Halloween candy has to be kept at a certain temperature. That makes sense too. So yeah, I do know that Commander does move some like consumables for freight. They did tell me that before, yeah. So reefer, a noun, a choral part. Okay. No
I'm gonna
jokes
have to
allowed
get
here. No,
going
we
kind
like
of soon.
we like jokes. What's that?
I'm gonna have to get going kind of soon. I
Oh,
haven't
that's
eaten
fine. I'm
today.
gonna have to go.
So.
I'm probably have to go too, because we've now grokked out how it is that you can add energy to an atom, a bunch of atoms, and get them to stop doing their thing enough that they're really, really freaking close to 0 Kelvin. And
Yep,
that's
yep.
pretty fucking cool,
Yeah, it is.
right? In more ways
Super
than
cool.
one. Yeah, because we don't do puns around here. Now, I'm gonna put out to everyone, including Dr. Tap, who's gonna have a great idea how to do this. Um, I was inspired by there's another content creator who probably doesn't know who I am, called the Kentucky Atheist, who's getting they're getting copyright claimed by Ray Banana Man and
Comfort.
Comfort. Yeah. So I was inspired to rewrite a song that's a well-known song about Ray Comfort, and it's called The Banana Man, and I did it with Billy Joel's Piano Man, and I sent that over to Dr. Tap, and I'm trying to figure out, because I have no musical ability of any kind, how can I make my new words to Piano Man into a great ode.
There's
To Billy
probably an
Joel.
AI for that, right?
There's got to be. I just don't know what it is. And I also realized I have this ode to Billy Joel, but there's a song called Ode to Billy Joe, which is who sang that? Man, she was amazing, that woman. Anyway, I gotta remember who sang that song, but she was amazing. Anyway, she sings a song called Ode to Billy Joe. And they're not related at all that I know of. Um, oh, PC is hitting buttons. Appreciate it. You have 54 credits towards mechanical engineering, and you're a machinist for 15 years. Commander, I am so confused as to where that came from. Oh, you know what? I understand. Commander is talking about precision. You have to be precise to do mechanical engineering, and you have to be precise to be a machinist. All right. Well, Dr. Tap's turned back into Weasel. Ready to pay though. Okay.
It's my final form.
Is your final form? All right. So we're gonna end the stream. We're gonna say thank you to everyone for coming and being here and watching all this. And I'm assuming Dr. Tap just he just exchanged the weasel that operates the head.
Don't ask questions
Right?
you don't want the answer to.
You know what? I think of the whole thing as basically like Voltron in a trench coat. Like a tiny little weasel in a color coded jumpsuit operating a mechanical cougar that when it stops being a mechanical cougar can then become the parts of a giant sword wielding robot.
Yeah.
And yeah, I love that shit. All right, I'm gonna end the stream and say thank you to everyone, and tune in next time, whenever that is, for another exciting edition of Al is Curious About Crazy Shit or whatever. We need a better name.
Okay.
Yeah, and Commander, you are correct. He's not just dishonest. He's I think that's a really kind way to put it. All right, bye everybody.